You're staring at your screen right now, reading these words, and you think you understand what's happening. Light from the screen enters your eyes. Your brain processes the information. You see letters, words, meaning. Simple enough. But let me ask you something that's going to unravel everything you think you know about seeing. What is light? Not the poetic answer, not the vague hand-waving about waves and particles. What actually is light at the most fundamental level? And here's the thing that should terrify you: nobody knows. We can describe what light does with extraordinary precision. We can predict how it behaves in every situation we've ever tested. We can manipulate it, bend it, split it, focus it, use it to transmit information across the planet. But what it actually is, the deep ontological nature of the thing itself, that remains one of the most profound mysteries in all of physics. And once you see how weird light really is, you'll never look at the world the same way again. Let's start with something you think you understand. Light travels. You flip a switch, light crosses the room, hits the wall. It moved from here to there. That seems obvious. But here's the question that breaks everything. What moved? When you throw a ball, the ball moves. It's an object traveling through space. But light isn't an object. It's not made of stuff in any conventional sense. So what actually traveled from the bulb to the wall? The standard answer is that light is a wave. Fine. A wave in what? When sound travels, it's a wave in air. The air molecules vibrate. That vibration propagates. You hear sound. When waves move across water, the water surface oscillates up and down. The pattern moves. You see waves. Every wave you've ever experienced is a disturbance in some medium. So what medium is light waving in? For a long time, scientists believed there had to be one. They called it the luminiferous ether, this invisible substance that permeated all of space, including the vacuum, and light was vibrations in the ether. It made sense. Light behaves like a wave. Waves need a medium, therefore there must be a medium. Simple logic. Except when they tried to detect the ether, it wasn't there. In 1887, Michelson and Morley did an experiment that should have measured Earth's motion through the ether. The Earth is moving through space, orbiting the sun. If there's an ether filling space, we should be moving through it like a car moving through air. And that motion should affect how fast light travels in different directions. Light moving with the ether should go faster. Light moving against it should go slower. They built an incredibly sensitive apparatus to measure this difference, and they found nothing. Zero difference. Light traveled at exactly the same speed in every direction, regardless of Earth's motion. This result was devastating. It meant there was no ether. Light doesn't travel through anything. It just travels through pure vacuum, through absolute nothing, a wave with no medium. That should be impossible. Waves are disturbances in something, but light is a disturbance in nothing. It's a self-sustaining oscillation of electric and magnetic fields propagating through empty space. The fields create each other. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. They leapfrog through space, supporting each other, needing nothing else. Light is a pattern that moves through emptiness. Not a thing traveling, but a pattern propagating. But here's where it gets stranger. Light also behaves like a particle. Not sometimes, not approximately, actually literally like a particle in certain experiments. The photoelectric effect demonstrates this perfectly. Shine light on a metal surface and electrons get knocked out. Classical wave theory predicts that if you make the light brighter, the electrons should come out with more energy, more intense wave, more energy transferred. But that's not what happens. The energy of the ejected electrons depends only on the frequency of the light, the color, not the intensity. Bright red light won't eject electrons no matter how bright you make it. Dim violet light will, and the electrons come out immediately, not after the wave has had time to build up energy. It's as if the light arrives in little packets, photons, each carrying a specific amount of energy determined by its frequency. High frequency, high energy, low frequency, low energy. The number of photons determines brightness, But each photon individually behaves like a particle hitting an electron and transferring its energy in one discrete chunk. So which is it, wave or particle? The answer is going to make you uncomfortable. Both. Neither. Light is something we don't have a word for, something that doesn't exist in our everyday experience. It exhibits wave properties when you do wave experiments. It exhibits particle properties when you do particle experiments. But it's not actually a wave in the classical sense, and it's not actually a particle in the classical sense. It's something else, something that our brains evolved to understand. Rocks and predators and food have no intuitive category for. We call it wave-particle duality, but that's just a name for our confusion. We're describing the elephant by feeling different parts in the dark. Let me show you how deep the weirdness goes. Take a single photon, one quantum of light, and send it toward a barrier with two slits. The photon goes through one slit or the other, right? It's a particle. It has to go through one slit. Put a detector at each slit to see which one it goes through. You'll find it went through one, never both. Each photon is detected at exactly one slit. Particle behavior. But now remove the detectors. Don't watch which slit the photon goes through. Send many photons through one at a time and look at where they land on a screen behind the slits. You don't get two bright spots corresponding to the two slits. You get an interference pattern, alternating light and dark bands. That's a wave pattern. That's what you get when a wave goes through both slits simultaneously, and the two waves interfere with each other, but you sent the photons through one at a time. Each photon went through individually. There was never more than one photon in the apparatus at once. So how did they interfere with each other? They didn't. Each photon interfered with itself. A single photon somehow goes through both slits. It's in a superposition, existing in multiple states simultaneously. But the moment you put a detector at the slits to see which one the photon goes through, the interference pattern disappears. The act of measurement, of observation, changes the outcome. When you're not looking, the photon behaves like a wave passing through both slits. When you are looking, it behaves like a particle going through one slit. The photon seems to know whether you're watching and changes its behavior accordingly. This is the measurement problem, and it's been driving physicists insane for a century. Now you might think this is just quantum weirdness at microscopic scales. It doesn't affect the real world. Wrong. Light is the reason you can see anything. Every color, every image, every visual experience you've ever had is photons hitting your retina, and those photons are carrying information about the world in a very specific way. When you look at something red, like an apple, you're seeing light that has a wavelength of about 650 nanometers. The atoms in the apple's skin are absorbing all the other wavelengths and reflecting only the red ones. Why? Because the electrons in those atoms can only exist at specific energy levels. They're quantized. An electron can be in this energy level or that energy level, but not in between. When a photon hits an electron, if the photon's energy exactly matches the gap between two energy levels, the electron absorbs the photon and jumps up. If the photon's energy doesn't match, it doesn't get absorbed. It bounces off. So the color you see is determined by which photons get absorbed and which get reflected. And that's determined by the specific energy levels of the electrons in the atoms of the object you're looking at. Color is quantized electron energy transitions. Every color you've ever seen is a specific electron quantum leap in some atom somewhere. The blue of the sky, nitrogen and oxygen molecules scattering short wavelength light. The green of plants, chlorophyll absorbing red and blue light for photosynthesis and reflecting green. The brown of dirt, complex organic molecules with overlapping absorption bands. Every color is a fingerprint of atomic and molecular structure. And your eye is a quantum detector, evolved over millions of years to be exquisitely sensitive to these electron transitions. Here's something that should blow your mind. The reason you can see it all is because atoms emit and absorb light in discrete quanta. If electrons could have any energy whatsoever, if energy levels weren't quantized, there would be no such thing as color. Everything would be a continuous blur. The fact that there are distinct colors, that red is different from blue, is direct evidence of quantum mechanics. You're seeing quantum effects with your naked eye every single moment of your life. But let's go deeper. What happens when a photon hits your eye? It strikes a molecule called retinal in the photoreceptor cells of your retina. That photon's energy causes the retinal molecule to change shape from bent to straight. That shape change triggers a cascade of chemical reactions that eventually produce an electrical signal that travels down your optic nerve to your brain. Your brain interprets that signal as light. But here's the thing. The photon itself is destroyed in that process. It doesn't bounce off your retina. It's absorbed. Its energy is converted into chemical energy, then electrical energy, then neural activity. The photon ceases to exist. So when you see something, you're not seeing light bounce off it and into your eye. You're detecting the absence of light, the shadow created by light being absorbed. What you perceive as vision is actually a map of where photons were destroyed. And there's a limit to this. Your eyes can detect individual photons. In complete darkness, a single photon hitting your retina can trigger a response. That's the quantum limit of vision. You cannot see anything dimmer than one photon. There is no half a photon. Light comes in discrete, indivisible chunks, and your eye has evolved to detect the smallest possible chunk. That's astonishing. The human eye is operating at the absolute physical limit of what's possible. Now let's talk about speed. Light travels at 186,282 miles per second in vacuum. That's the speed of light, and it's constant, always the same, regardless of who's measuring it or how fast they're moving. But here's the question nobody asks. Why that speed? Why not twice as fast? Why not half as fast? The answer is that the speed of light isn't really about light at all. It's a property of space-time itself. Space-time has a maximum rate at which information can propagate, a maximum speed for cause and effect. And that maximum speed is what we call the speed of light. Light travels at that speed because photons have no mass. Anything with zero mass must travel at the maximum speed. It has no choice. But from the photon's perspective, and this is going to break your brain, no time passes. A photon is emitted from a star 1 billion light years away. From our perspective, it travels for 1 billion years before reaching Earth. But from the photon's perspective, the journey is instantaneous. It's emitted and absorbed in the same moment. No time elapses. The photon doesn't experience duration. It doesn't have a reference frame in the usual sense. Time dilation at light speed is infinite. The photon exists outside of time. Think about what that means. Every photon that's ever hit your eye, whether it came from the sun 8 minutes ago or from a galaxy billions of light years away, from the photon's perspective, the trip was instantaneous. The entire history of the universe from the Big Bang to now, from a photon's perspective, happens in a single timeless instant. Photons don't age. They don't decay. They don't experience time. They're messengers from a timeless realm carrying information across the universe in what to them is no time at all. And here's where it gets truly strange. Light doesn't just carry information. Light is information. When you see an apple, the information about the apple's shape, color, position, all of that is encoded in the pattern of photons hitting your retina. The photons carry that information from the apple to you, but the photons don't contain little pictures of the apple. The information is encoded in the pattern, the distribution of wavelengths, the intensity, the direction. Your brain decodes that pattern and reconstructs an image, but the image isn't in the light. The image is in your brain. The light is just data. This is why optical illusions work. Your brain is interpreting patterns of photons, making assumptions about what those patterns mean. When the assumptions are wrong, you see things that aren't there. The light itself is unambiguous. The pattern of photons hitting your eye is what it is. But your brain's interpretation of that pattern can be fooled. What you see is not what's out there. What you see is your brain's best guess about what's out there based on the pattern of photons hitting your retina. Now let's consider where light comes from. Every light source is fundamentally the same process. Electrons changing energy levels. An electron in a high energy state drops to a lower energy state. The energy difference is released as a photon. The energy of the photon, and therefore its color, is exactly equal to the energy difference between the two levels. This happens in the sun. Electrons in hydrogen atoms in the sun's core are constantly being excited to higher energy levels by the intense heat. When they drop back down, they emit photons. Those photons bounce around inside the sun for thousands of years before finally escaping and traveling 8 minutes to Earth. The light you see from the sun was created in quantum transitions thousands of years ago, then spent 8 minutes crossing space to reach you. It happens in fire. The heat excites electrons in the burning material. They drop back down, emitting photons. The color of the flame tells you which elements are present. Yellow flames, sodium. Blue flames, carbon or hydrocarbons burning completely. Green flames, copper. Each element has its own unique set of energy levels, so each element emits its own unique set of wavelengths. You can identify elements just by looking at the light they emit. This is spectroscopy, and it's how we know what stars are made of. We can't touch a star. We can't go there and take a sample. But we can analyze the light, see which wavelengths are present and which are missing, and determine the chemical composition from millions of light years away. It happens in LEDs. An electric current pushes electrons to a higher energy level in a semiconductor. They drop back down, emitting photons. The energy gap in the semiconductor determines the color of the LED. Change the material, change the color. It happens in your body. Fireflies produce light through a chemical reaction that excites electrons. Bioluminescence. Deep-sea creatures do the same. Even your own body emits a tiny amount of light, too faint to see with the naked eye, but detectable with sensitive instruments. You are glowing right now. Every warm object emits infrared light. That's thermal radiation, photons emitted because electrons are being jostled by thermal energy. Every source of light is electrons transitioning between energy levels and emitting photons. That's it. That's the only way to make light. Everything else is just different ways of exciting electrons. And when light is absorbed, the reverse happens. A photon hits an electron. The electron absorbs the photon's energy and jumps to a higher energy level. The photon is destroyed. Its energy is now in the electron. That's how solar panels work. Photons hit electrons in the panel, exciting them to higher energy levels. Those excited electrons create an electric current. Light is converted directly to electricity. That's how photosynthesis works. Photons hit electrons in chlorophyll molecules. The excited electrons drive chemical reactions that convert CO2 and water into glucose and oxygen. Light is converted to chemical energy. Plants are powered by quantum transitions in chlorophyll. So here we are. Light is a self-sustaining oscillation of electric and magnetic fields, propagating through empty space at a fixed speed determined by the structure of space-time itself. It behaves like a wave in some experiments and like a particle in others, but it's neither. It's something our brains aren't equipped to visualize. It carries information encoded in patterns of wavelength and intensity. It's created by electrons dropping between quantized energy levels and destroyed when absorbed by other electrons. It doesn't experience time. From its perspective, the universe is timeless, and every visual experience you've ever had, every color, every image, every sight, is your brain's interpretation of patterns of these strange quantum entities hitting your retina. We can describe light with phenomenal precision. Maxwell's equations predict electromagnetic waves. Quantum electrodynamics predicts photon behavior to absurd accuracy. We can manipulate light, use it, bend it to our will. But what it actually is, the deep nature of this thing, remains mysterious. We have equations that work. We have models that predict. But the ontology, the fundamental whatness of light, that's still unknown. And maybe that's okay. Maybe the question itself is malformed. Maybe asking what light is in terms of something more fundamental is like asking what the number 3 smells like. It's a category error. Light is fundamental. It's one of the basic constituents of reality. And everything else, including vision, color, and nearly all information we have about the universe, is built on top of it. So the next time you flip a light switch, remember, you're not just illuminating a room, you're triggering quantum transitions that emit photons, self-propagating disturbances in electric and magnetic fields that travel through nothingness at the maximum speed allowed by space-time, carrying information in patterns your brain evolved to decode, creating the experience you call sight. And the fact that we understand any of this, that we can predict it and use it, is one of humanity's greatest achievements. But the mystery at the heart of it, what light actually is, that remains. And maybe that's the most beautiful part of all.